In this video, we will talk about the hypothesis testing for the population mean. In the last two videos, we talked about the first one was the hypothesis test, and the second video was about the population proportion. Remember from chapter 7, we talked about the proportion first, then the mean, and lastly was the standard deviation or variance. Now this section in the package 10.3 in your textbook, it should be 8.4. So we'll learn about some hypothesis testing for the population means. Remember, for the last video, when we talk about the proportion, we use the Z statistic, but for the mean, similar to chapter 7, we have to use the T statistic or student T statistic. Now let's go over this section. So to test the hypothesis regarding the population mean, and we assume that the population standard deviation is unknown, we have to use the T distribution or T statistic distribution instead of the Z from the last section. Now when we replace the sigma with S, and S is a standard deviation, that you can use any of the TI 83 or 84 and input the data and to find the standard deviation. If you use the student T distribution, make sure you have to know the degree of freedom, n-1 degrees of freedom, and n is the total number of the sample that you have. So T is the x bar minus mu over S divided by square root of n. We have to use this throughout this section. Now, similar to the population proportion, there are some requirement needed to do the testing in order to use the p-value. You have to make sure that these are correct before doing the procedure. Now the first one is that the sample size must be obtained from the simple random sampling, and there should be no outliers, or the sample size is large, which is 30 or above, then it should be good, and the sample values are independent of each other. And usually these requirements are met in this class for our testing. So how do you construct the hypothesis test about the mean? Again, we still have three cases: the two tails, left tail, or the right tail. The first is you have to use one of these three ways and see which one is met for your problem. The second step is you have to select a level of significant alpha, and usually alpha is given from the problem, and this is the seriousness of making a type 1 error. Once you have that, you can compute the test statistic T0, which is the formula we just talked above, and make sure that n here they follow all the T distribution with n-1 degrees of freedom, and then finding the p-value using the T CDF function on TI 84, probably 83 will have it, I'm not sure, but TI 84 should have it. Now two tails, that means you are taking the value at the 2n. The way we do that is we multiply by 2, and we take the value greater than T0, and we multiply by 2 so that you can double count for this one. If t is less than t0, then we use the left area, or rather than we use the right area. Now the commands for the tcdf function is that you have to use the input tcdf on TI-84. The first input is the lower bound, then the comma the upper bound, and then the number of the real freedoms. And you have to state the conclusion after that. That means if the p-value less than the significant level alpha, then you have to reject the null hypothesis. If the p-value is bigger than the alpha, then do not reject the null hypothesis. So the goal is we have to be able to reject or not reject the null hypothesis. This is the given data, given facts, and we want to prove something else is correct or not. So that's why we come up with the p-value, and if it's really small, less than alpha, we reject. If do not, we do not reject. And note that the procedure is very robust, which means that minor departures from the normal curve won't affect any of the results of the test. However, for the small sample less than 10, the procedure should not be used if we have a lot of outliers. So pay attention to this. Okay, so let's go over the first one and see how it's going. So this one, we have the large sample. So testing a hypothesis about a population mean, assuming that the resting metabolic rate RMR of a healthy males in complete silence is 5,710 kilojoule per day. Now this is the fact, the given info we already know, so this should be the null hypothesis. Okay, now the researchers they measure the RMR of another or many different 45 randomly selected healthy males who was listening to calm classical music, and they found their mean to be this value instead of this one. So they make the claim to be this, so this one is the alternative hypothesis, and they also have the standard deviation of that 992.05. Now with the significant level alpha to be 0.05, is that evident to conclude that the mean of the male that are listening to the calm classical music is different than the given fact or the null hypothesis. Okay, so they give us the standard deviation here. This should be the S standard deviation from the t-statistic formula. Now they give us the mean, the new mean, which is X bar, right? And they also give us the initial value, and usually the one that's given from the beginning of the problem was the null hypothesis. Okay, this is the mean. Now the question is, it has enough evidence to conclude that the new finding is different from the null. So the key word here is different. The different, that means not equal, and not equal we have to use the two tail, right? Two tail, they are different from the null hypothesis because they don't mention anything about less than or bigger than, but they said different, so we have to use a two tail. Okay, so this is the given info. Now this is a simple random sample because we have randomly selected, so this is good. The n, we have 45 sample here, so it's bigger than or equal to 30, so that's good. We have a large sample size. Now since the sample size is less than 5% of the population size, all the males, this is very small number of the males, so it's of course it's less than 5%, so the assumption of independent is also met. Usually this condition you don't have to worry much in this class. Now set up the hypothesis testing. The null hypothesis is the one that given from the problem, which initially we have 5, 7, 1, 10 kilojoule per day, so that is the null hypothesis, or H0. Now H1 is the alternative hypothesis, or the one that we came up. We claim that they are different. That means the new one, they are different from the original one, right? This is the null one, null hypothesis. This is the new one. We claim that this is different from that. And the significant level, in this case, they give us 0.05. Normally it's 0.05. Now, we have to, after we gather all the info, we have to compute the test statistic, or T0. So X bar is the one that they came up with, or 5708.07, the new mean, right? So X bar is the mean, the new mean that they came up with. So we have 5708.07 minus mu naught is usually mu naught is the null hypothesis, which is this value. So 5710 over S is the standard deviation, or it is here 992.05. So 992.05, and over radical of n, which is 45. If you plug in that to any of the TI calculator, you should get minus 0.013. Now after you have the T naught, or the test statistic, you're gonna draw that on the curve. So this is the curve. 0.0 minus 0.013 is here, right? Because this is the two tails, right? This different, meaning the two tail. That means that you are taking the value at the two end tail. So one is minus 0.03, the other one is 0.013. So we are taking all the value after that, the minus 1, and also all the value of the plus 0.013. So you want to find all the area of the two right and left and tails. Now that is your p-value, is the area under the curve. So the p-value, so in order to find the area, you just have to find the area of one of them and then multiply by 2. So I multiply by 2 and I multiply. Now in order to compute the area under the curve, use the command TCDF on your calculator TI-84. Now the command for that was lower bounds, upper bounds, degrees of freedom. Okay, so maybe I'll use this value. I'll compute the area under the left curve. So the lower bound is all the way to the left, so very small number, and we usually use minus infinity, but there's no infinity symbol, so we can use minus 10 to the power of 99. Okay, that's very small number. Now the upper bound is minus 0.013, 0.013 minus, and the degrees of freedom, which is n minus 1, right? N minus 1, n is 45, n minus 1 degree of freedom, so n is 45, so we have 45 minus 1 is 44, or just 45 minus 1 I write here. If you do the calculation on the TI-84, you should get 0.990, and this one is bigger than the level of significance, 0.05. Because it's bigger than that, we do not reject. Okay, so the conclusion, if we do not reject, that means there is not enough evidence. So there is insufficient evidence at the level alpha 0.05 to conclude that the mean of the males listening to calm classical music is different from that amount we originally have. So different. Okay, so let's go to the next example. The previous example was large sample size. So go back here. We have large sample size. Now in this case, we have small, right? Small sample size. And let's see how we're doing with the small sample size. According to the United States, mint quarters weigh 5.67 grams. Now this is the original data, the given, the fact. So the original value usually it should be the null hypothesis. Okay. Now a researcher or a new scientist is interested in determining whether the state quarters have a weight that is different from 5.67 gram. Again, they claim that the new one they are different. So again, this problem is also kind of also the two tails, right? Because they claim to be different. So different, that means not equal. We are using the two tail from the original null hypothesis 5.67 grams. So they claim that this is different, and the way they do that is he randomly selects 18 state quarters, weighs them, and obtains the following data, 18 of them. With a level of significance 0.05, is there enough evidence to conclude that the state quarters have a weight that is different from 5.67 grams? So before doing anything, first we must verify the requirements to perform the hypothesis test. This is a simple random sample, yes, because we have randomly select, right? Now the n, we only have 18 data, 18 states here, and 18 is less than 30. So since the sample size is small, we must verify that the data come from a population that is normally distributed, okay, with no outliers. For all the problem in the chapter, you don't want any of the outliers. It will mess up everything and won't give you an accurate result. Now the sample size is very small, so it's also independent. This condition is usually met. Okay, so the next question is, how do we verify that the data come from a population that is normally distributed with no outliers again? And you can do that by normally probability plot all the data, and you see there's no outlier here, or you can plot, which is the linear, so no outlier, or you can use a box plot. Usually I'll tell you whether the data has the outlier or not, so you shouldn't worry much about this. But you can use the TI graphing to graph the plot here. So from the normal probability plot, the data is approximately linear, and there's no outliers, so you should be good. Usually I'll tell you if you have the outlier or not, so don't worry much about these plots here. Now let's try to solve the problem. Now the null hypothesis is 5.67 grams, the one that they gave us originally, and then we claim that the quarter new, the new one, is different from the null hypothesis. The level of significance again 0.05. Now you have to compute the test statistic, which has the formula again, same thing. So how do I compute the test statistic? So let's come up here. Okay, you have all the data here, 5.70, 5.67, 5.73, and so on. So in order to find the x bar or the mean value here in the test statistic formula, this is the mean. So in order to find that from this sample, you're gonna add all of them together. So 5x bar, you're gonna add 5.70 plus 5.67 plus all of them together until the last one, and you're gonna divide 18 because there are 18 of them, and you should get 5.7022, right, around that. So now that is the x bar. So we come down here and we compute the test statistic. So x bar is the one I just had above, so 702. Let's just pack 3 decimal places, minus this one is a null hypothesis 5.67, and over S is the same the standard deviation. So you can use the TI-84 and using those 18 value, you can find the standard deviation from that, and it should be 0.0497. This is obtained from the calculator also, the standard deviation of those 18 samples, and n here is 18, right? And this is around 2.753. This is the test statistic. Now once you have that, you can find the p-value, but before that, let's draw the curve. This is positive, so it's on the right side, right? So this is 2.753, and the other left side should be negative of that 53. So this is two tails problem, so we need to find the error under the curve. Now I just have to find one of them and multiply by 2. So the p-value I can multiply by 2 using the TCDF command also, right? Now the lower bounds, I may just take the the right hand side region this time. So the last example we use a negative something, the left region, and we multiply that by 2. But now let's try the right region, the right hand side, positive 2.753. So the lower bound is from that point 2.753 all the way to the right. So the upper bound is very large number, and I told you guys to use 10 to the power of 99. And then the numbers, the n minus 1 degrees of freedom, and it's 18 minus 1, so it should be 17, right? And this turned out to be 0.014, and of course this is less than 0.05, the significant level. So less than, we reject them. If we reject, that means there is sufficient, there's enough evident that at this level of significance to conclude that the mean weight of the state quarters they differ from the original suggested value. And here again we have all the instructions for checking your hypothesis test using TID4. You can do the reading on that. And this is the end of section 8.4.